Dear students, welcome to the course on circular spaces. In this course, we will mostly introduce the sublow spaces, starting from its basics from distributional derivatives and so on, and then probably end the course with some applications of the sublow spaces. So let's start with the motivation or the need to look into such spaces. Why study such spaces? Okay. So firstly, there are three reasons why we need to study sublow spaces. Firstly is the idea to generalize the notion of function. So classically, we know that a function is a relation from one set to another set, right? Where for each value it can take exactly one value, right? It cannot be multi-valued, which is a relation, whereas function is different. So that's the classical notion of function. We need to generalize the notion of function, and once we generalize the notion of function, we have to extend the notion of derivatives and so on to this generalized notion of functions. And then the last reason being that we need to, when we study differential equations, we have a notion of solution for a differential equation, where we usually say that the function has to satisfy the differential equation. In other words, it has to be as many times differentiable and so on, and then satisfy the equation. We have seen situations in differential equation where restricting ourselves to that notion of solution is actually too restrictive. One needs to generalize the notion of solution. So all that is the reason behind developing this entire theory. So instead of saying this, let me just recall via some examples or cases where you actually encounter such situations, all these three situations. Okay. So let's look at these via specific examples. Firstly, why should one generalize the notion of function? Okay. So this practically was found when Dirac was working with this quantum theory of collision, and then had ended up an equation which involved a function which does not fit into the mathematical notion of function. Okay, I will describe that later. But just to give a simple case, let's consider this example. So consider a particle of mass m, right? So let's say this is the x-axis, right? So it's moving along x-axis. So there is some particle, let's say, okay, and let's say it's moving in this direction v with the velocity v, okay, speed v. Fine. So now if it's doing that, then what we say that at time t equal to t naught, it has a collision with a vertical wall. Okay, let's say. So what I'm saying is that there's a particle which is moving with velocity v. There is a wall, and it kind of hits this wall at time t naught, let's say. So what happens if it hits? Once it hits, the particle will return. Okay. Here I am assuming that the particle does not break after hitting and so on. It's like kind of elastic collision. So the particle hits and then it returns back. Okay. And when it returns back, it's in the opposite direction, and it returns with this same velocity. So in this case, opposite directions minus v, let's say. Okay. So this is a situation we want to model. Okay. So there's a particle which is moving in this x-axis along this positive direction, hits the wall here at time t equal to t naught, and then bounces back with the same velocity in the opposite direction. Okay, that's the situation that we are trying to model. So the particle has an elastic collision with vertical wall and bounces with the particle speed being minus v. Okay. Now, if you try to model this situation, what we know is that force is mass into acceleration, right? So here, if v1 and v2 are the speed at time t1 and t2, right? Then the total force acting on the particle is this, right? Sum over all the forces acting at all the times between t1 and t2, and then this is the mass of the particle, and this is the acceleration that it might have, right? At time t2, its velocity is v2, and at time t1, velocity is v1, so the difference. Okay. So now, this is the situation. In our case, we had assumed a constant speed v, and after collision it has a constant speed minus v. So suppose we take the two time instants t1 and t2 which are less than time t0. T0 is the time at which the collision happens, right? So if t1 and t2 are before the time t0, then what is the speed? The speed is v. Okay, the speed is v, which means that v2, v1, so this, which means the left hand side here is 0. Okay, left hand side here is 0, which means this integral is 0, that is no other force is acting on it. Similarly, if the time t1 and t2 are after the time of collision, in which case the speed is minus v, and in that case also the LHS is 0. Okay, whereas if the time t1 and t2 is chosen before and after collision, okay, suppose t2 is a time before collision and t1 is the time after collision, then what happens here? This becomes 2mv, which is clearly not equal to 0 because none of them is 0 here. So this is not equal to 0. So LHS is not equal to 0. So what do we have? We have that in the situation here, right? For this situation, you have a non-zero value, and in every other situation, the RHS is non-zero, and every other situation the RHS is 0, right? Now, is that possible? That's not possible, right? Because if you want a f such that this integral is 0 at every point except at one point, that is at t equal to t0, right? f of t for all t which is not equal to t0, it comes out to be 0 from the previous equation. And now at t equal to t0, there is a collision happening, and that has to be non-zero, which means f is a function which is 0 everywhere except at t0 and non-zero at t0, right? And the integral of that has to be 0, right? That's what we know from even Lebesgue integration, right? That's the most advanced integration that we have, which tells you that it doesn't matter what is the value of f is on measure 0, so the integral is 0 because f is 0 almost everywhere, right? Whereas the right hand side is non-zero here, right? So classically you do not have a function f such that this equation is satisfied. So to model this situation, which is actually called a mechanical impulse, to model this situation, you cannot do it by a classical function f. You need to generalize the notion of function. This is the kind of situation which actually came about in some Dirac's Dirac's work. For instance, when he was working on his quantum theory of collision processes, in fact, this is the work for which he actually got his Nobel Prize. So when we're working, he actually derived one equation, which is the derivative of log x. And what he derived, the equation that he derived was derivative of log x is 1 over x minus I is the complex imaginary I, right? Complex I, and delta pi is the usual pi, and delta x. This is the equation that he derived, okay? And the delta here, he claimed, is a function with these 5 properties. Now, classically, this doesn't make sense, and this is why mathematician couldn't accept such a relation. I mean, initially, but then physically it made sense. It led to improved understanding of the collision process, and I mean everything. I mean, it kind of, I mean, one could not junk this work, though the equation looked kind of nonsense, right? So what he said about this delta was that this delta is 0 x everywhere except at 0, which means it's a function which is 0 everywhere except at one point, which is x equal to 0. So it's a 0 almost everywhere function. But then he said the integral of that function should be 1, right? Doesn't seem to make sense, right? And then he said this delta has this property that if you integrate it with a product of any function f, it gives you the value of f at that point where it is concentrated, where this delta is concentrated. And then he also said delta is infinitely differentiable, and that derivative has this relation. He also said that this delta is nothing but the derivative of the step function, and step function itself, now we're talking of derivative of step function itself, doesn't make sense mathematically in those days. So this was, you see, in late 1920, that is around 1929, 28 and so on. So all these 5 equations was mathematically not making any sense, right? So, but then this physically made sense, so one has to give meaning to this, and that is how the idea of trying to generalize the notion of function, I mean, all these need to generalize the notion of function came in. Here again, you see, even before the work of Dirac in around 1902, Lebesgue had already introduced the notion of measure theory and Lebesgue integration, right? I mean, so in the context of Lebesgue integration, he had already introduced the notion of measures. Now, in that sense, one could what we today call the Dirac measure can be defined, and one can make sense of this first 2 properties in the sense of Dirac measure. So, if one incorporates Lebesgue's theory, one can make sense of the first and second property, which fits in with whatever Dirac wanted, right? But then again, in fact, even this, actually first, third, 3 properties, not just 1, 2, even the third property. Up to this, one can make sense using the measure theory. But the infinite differentiability and the derivative, and delta being the derivative of the Heaviside function, which is a step function, this was still, it's still an issue that doesn't come from measure theory, right? So this example illustrates why one should generalize, why the need for generalizing a function came in, and then the property 4 and 5 is actually one particular motivation of why one should try to generalize the notion of differentiability to the generalized function. Okay, that is the first motivation that we are talking about, and second as well, but little bit. I'll give one more example for why. So the properties 4 and 5, which we saw on the previous slide, were already giving an example of why we should generalize the notion of derivative to generalized function. In addition, I can give some more. If you look at the transport equation, which is a first order PDE, right? If you look at the transport equation, you can actually solve it using even a simple change of variable or even the standard, which is the method of characteristics. So if you use this method of characteristics to solve this first order PDE, you will end up with a general solution which is of this form. Okay, where this f can be chosen from the initial condition. So usually you will have ut, let's say minus ux equal to 0, let's say in some interval or in whole real line, let's say in R, and then you have this initial condition, let's say u naught of x, right? And then from this f will become then this u naught, that initial data that is given. So this is something, if you have come across method of characteristics, you will know that this is the solution. This is a general solution. If you ignore the initial data, this is the general solution, right? And with the initial data, you actually obtain this f. So if you actually know this theory, you would know that what is this actually saying is that the linear transport equation actually tells you that if this is the time t equal to 0 line, okay, time t equal to 0 line, this is the time variable, this is the x-axis, then at time t equal to 0, you are given u naught, so you have some graph just lying above this line, okay. And what is the solution is saying is that, let me draw in a, I don't know, let's see. So basically this is, let me draw in a possible 3D, okay. So this is on the plane T, okay, and then this is the line, this is the, so you have some function u naught, this is your u naught lying at time t equal to 0. So what is this solution telling you? This solution is telling you that at time t, the solution is nothing but a similar graph like this, where this or this is of slope is minus 1 over c or something, right? Minus 1 over this slope, so line with this slope. So basically it's saying that the solution is constant along this characteristics line with slope 1 over c here. So whatever initial data you have, it is just shifted along the characteristic lines. That's what it means, right? Which is what the solution of the transport equation means. So usually why am I describing all these things here is that, which means that if you want your u to be a solution to this, if you want your u to be a solution to the transport equation, then you have to choose f such that it satisfies this equation, and this equation is a first order PDE. That means you would have to choose f in C1. It should be at least once differentiable, right? So that you can differentiate and then satisfy this equation. So that automatically imposes that the u naught data that you choose here for the transport equation has to be a smooth function, has to be a nice function. Okay, you have to be able to differentiate this function. Now the point here is, what instead of u naught, I start with let's say a step function like this at t equal to 0. If I start with this, then automatically you can see that after time t, my solution should also be, if transport equation physically means this, then it basically means that after time t, right, after time t, this is the kind of it has to move along these characteristic lines. right? My solution would be this, right? But then this is not an admissible solution because this is not even a continuous function. This is a kind of discontinuous function. One cannot even verify these equations. So what is the practical problem here? So though physically this seems to make sense, this, I mean, taking a discontinuous initial data and maybe the theory works, but then the fact that the model problem that we have, so the equation that models this situation is actually a differential equation, restricts the notion of solution here, right? So this is so which means that if we can generalize the notion of derivative to functions like this, which are not classically differentiable, and we somehow change our interpretation of the differential equation in those sense, then probably we can include these discontinuous data situations, right? Discontinuous solution situations. So that is another motivation. Okay, and then finally, this is what I have described already. So the mathematical mathematical rigor is what makes the choice of f for the initial data. I mean, imposes the smoothness conditions on the initial data and so on. Because to begin with we have a differential equation, so we need to have the solution as many times differentiable. Okay, so all that I have explained already, that if we take a Heaviside function as a step function, then mathematically how does one describe this kind of a solution? Though it physically it looks like a solution, but mathematically one cannot include that as a solution, right? So how do you handle such situations? Okay. Now the third case, the motivation that I was talking, is the case of weakening the notion of solution. So where does such situation arise? So let's consider, if you have seen method of characteristics, first order or even conservation laws, you must have come across the Burger's equation. So in the Burger's equation, you have, this is like the linear transport equation, but just that instead of C, you have the unknown U here. Okay, you have an initial data. So if you go through the method of characteristics, you can actually find that the general solution is given in the implicit form. So U is U naught, where U naught is the initial data, and this unknown U again appears inside this as an argument. Okay. So if you know from the method of characteristics, you know that this is the solution of this initial value problem, the Burger's equation, and the solution is such that it is constant along the characteristic curves, which are given by this equation. And these curves, so if you actually plot them, so these are curves which has slope 1 by u0 of r. See the transport equation, it was minus 1 over c, right? Which means the characteristic curves all had the same slope. So they were all like parallel lines emanating from the x-axis, right? Like this. This was a situation in the previous case. Whereas now in this situation, this line, which is eminently, suppose this is r, then the slope of this line is u naught of r. Similarly, if this is r2, the slope of this line is u naught of r2. This is r1, let's say. So the slope of these lines are all changing depending on the point that you start with, because of the non-linearity that you have in the equation. Okay. What is the issue with this, with such a thing? And along these curves, the value is constant. So what happens is, think of a situation where the given u naught is such that for 2 points r1 and r2, let's plot r1 and r2, r1 less than r2. So if in that case the value of u naught at r1 is bigger than the value of u naught at r2, what happens then is that 1 over u naught of r2 is bigger than 1 over u naught of r1, which means the slope of the line passing through r1 is smaller than the slope of the line passing through R2, which means the slope of this line could be this and the slope of this line is like this, which means these two will necessarily intersect at a point, right? Because they are no longer parallel lines now. Now, what is the issue with this is that what is this saying? That the solution is constant along the characteristic curves, which means it's constant along this line, it's constant along this line. So the value here is u naught of R1, the value here is u naught of R2, and if these two values are not same, you have a multi-valued situation here. Right? This is what you must have seen already when you did method of characteristics and so on in your PD course or something. If you have not seen, please go and have a look. So in such situations, how do you handle? How do you get a solution? So you don't have a solution for all time t, right? Because after this stage you cannot get a solution. You don't even have a proper function. So that is where you have situations like, so depending on the problem, so you can use rarefaction, you can use this Rankine-Huguenot condition and so on to extend the solution to all time t in some possible way. But the issue there is whether the solution that we extend is kind of the physically relevant solution or not. Right? So these are the issues there when you actually extend the solution outside the normal course. So these are the situations where, so to obtain a physically relevant solution, to include these type of solutions where the method of characteristics stops to work, is where we introduce the notion of weak solution and so on. Okay, so if we relax the notion of solution, one can actually see this partial differential equation in a different context and try to get a solution in that context by weakening both the differential equation and the notion of solution. Okay, so that is the third motivation. All this I have explained. So this is the situation where you will have the multi-value. So if you choose different value for if you choose u naught such that they take different values like this, then you actually have a multi-value. So at one point, this is the point of intersection x naught t naught. Okay, so even if you, so in this case you see u naught could be a smooth data. You don't have to start with the discontinuous data. Even with the smooth data, you may not be able to find a solution for all time t, and you may have to do something more to actually obtain a physically relevant solution, and that you can do only by weakening your notion of solution. So these are the motivations on why we have to study whatever we have to study in this course. Okay, some we need to kind of start with. Okay, then one can motivate it in many ways. So I have done it this way. That's it. Okay, so now let's get into the other basics that is required for this course. So the next thing is, once I want to generalize the notion of function, you see when I say a function, say some from set A to B, then there is a set for argument. It takes some x to f of x. So you have an argument for this. So when we are going to generalize the function, we are going to see later that the argument for the generalized function is what is called the test function space. It's called test function because you are going to test this function. So you are going to test this map with element from this space. So the argument for the generalized function will be the space of test functions. Okay, we will introduce what is space of test functions in some due course. Okay, so what is the motivation? How do we do this? So what is the idea? The idea is that we need to generalize the notion of function such that to that generalization you can also generalize the notion of derivative. Now the classical derivative has one nice property, which is the integration by parts, right? So you know this is the integration by parts form, right? So if you take an f which is in C1, and if you take a phi in C1, so you can do this for, so you fix f and you can vary phi. So this result is valid anyway. This equality is valid, right? So you take an f and you take a phi both in C1, I'm just giving the example here for one dimension, okay, because that's how we'll start, but then we'll generalize it to, we will motivate, so this is just for the motivation purpose, right? So take C1 and C1, and by the integration by parts tells you that phi f prime integral is this, right? So here, if instead of choosing phi from C1, if I choose in a much smaller class, which is C1 compactly supported, that is the support of this function is compact in AB, that means at the endpoints, the function will vanish, that is at A and B, which means phi B and phi A is 0, so you actually have phi equal to 0. So what you actually have is this thing is equal to minus of this thing, okay? Why is this important? What does this tells you? That you actually have so you have a function f and you have the derivative of f prime given in terms of something where the derivative of f is not involved, okay? So this is the motivation for generalizing. So here you have a property of derivative, and this property of derivative is what we will use to generalize the notion of derivative for generalized functions, okay? So this is just a motivation. You will understand it better as we go through the course, but I'm just motivating now why the choice of test function has to be something particular, okay? So what we do is that we just take phi to be compact support, then you remove this whatever you make it 0, and then you have some relation between f phi and f prime phi, and so phi prime and so on. Now this integration by parts is actually valid. Now this is what I said. So if I take compact support, I get this relation, okay? Now if instead of taking f in C1, if I take f in Ck and then phi in compactly supported, earlier I said C1, now you see that if I have to do this differentiation k times, I need to choose k, but I'm going to do this for allow it for any k. So for simplicity, I'm going to take infinitely differentiable. So phi is C infinity C A B. Then in that case, this formula you have becomes this. So the idea to show you these steps is to actually tell you that the classical derivative has a property if you apply it for some special class of function, sense that if you take this infinitely differentiable compactly supported function, then every function f and its derivative has some relation in terms of the derivative, where the derivative of f is pushed over to the as derivative over phi. What is the idea why we need to do this? The brilliant jump here is that you can actually identify f with this linear map, right? So when you do that, and if you choose phi to be from this class of functions, then both the integrals appearing here, both this LHS integral and the RHS integral, both can be seen as linear maps on this space. Okay, this is our space of test functions that we will see later. I will elaborate on that further. So this is the reason. So I'm motivating why this choice of functions, right? This choice of functions is precisely to ensure that from integration by parts you actually have a relation in terms, for the derivatives. Okay, so this is the space of test functions. So now once you think of this map, that is this map, as a map from CC infinity of AB to R, right? If you think of this as a map from CC infinity, so basically it's and it's a linear map. You can very easily check, right? It's a linear map. So it's a linear functional on the space of all infinitely differentiably compactly supported function. So it's a linear function. Now, if we look for a topology, suitable topology which is complete, suppose we can put a topology in the space which is complete such that this linear functional becomes continuous, okay, then we have identified f with this linear functional. So what we have done is a kind of generalization of the function. You started with a function, because any generalization that we do finally has to coincide with the classical notion, right? So here I started with a classical notion of function, classical function, and I've identified a linear, so a continuous linear functional. I'm not yet done, I'm just motivating here. So I'm just saying if I can find a topology, suitable topology which is complete, and under that topology, if this functional is continuous, then that continuous linear functional will identify with the f that we started with, right? So suppose I call this map as TF, then what we have done is that we have identified f with TF. Let's not use this. We have identified f with TF, where this f is a classical function, whereas this is a continuous linear functional on the space of all infinitely differentiable compactly supported function. Okay, so can we do that? So we need to find, so first we need to understand this function space, try to get a suitable topology, and then if we can do all this, then we have generalized the notion of function. Okay. So before we seek a suitable topology which will make this linear functional continuous, what are the elements of this set? So far I have been working with AB, now I have jumped into all dimensions. So AB is an interval, right? AB was an interval in R, right? Now omega is a open set in the Euclidean space Rn, right? So one can define. So what is here? You know, it's infinite differentiable compactly supported function on AB. What about here? Here it basically means it's the set of all functions, continuous functions, whose all order partial derivatives exist, and the function is compactly supported in omega. Okay, that's what this means. So, but what are the elements of the space? We need to understand, right? What are the elements of the space? Can you even think of an example of a function from the space? Right? Try thinking and try doing that on your own before you proceed with the lecture. Try to think. Of course, there is zero function is there. Other than that, a non-trivial function. Right? You need to think of an example of a function from the space which is not zero. In fact, you can even verify that this is a vector space. So this is a vector space of functions. So zero is there. That's not an issue. Okay. So that's what we are going to look at. We are going to look at the elements of the C infinity C omega. So let's before that understand what is C infinity. As I've already said, C infinity is a space of all real valued functions whose partial derivatives of all order exist and are continuous. Okay. For instance, all multiple polynomials, trigonometric functions, exponential functions, they are all C infinity, right? At least in one variable, you know, they are all C infinity. Now, C infinity C omega is the subclass of C infinity omega that are compactly supported. So the C means that they are infinitely differentiable functions that are compactly supported. So we want to find elements of the space. Okay. So any function. So how does any function in C infinity look like any function will fall to 0 within a compact set because it's compactly supported. Suppose say this is omega, and suppose you say there is a, I mean that's not a good, let's take this. Suppose say this set K, this is the compact set, right? So any function will be such that it has to be non-zero here and should become 0 in a subset of K. Basically it should become 0 within K and then become 0 everywhere. So this is how, so if you think of the graph of this function, it is 0 everywhere and then suddenly there is a bump just above K, right? Some kind of mountain above K, and then it falls to 0 as we approach to the boundary of K, right? And then it becomes 0. So most of these, so any function that you can imagine in CC infinity omega will be a bump function. And because they're infinitely differentiable, they have to be smooth, right? They cannot have edges or sharp corners. So what is the example that you can think of, right? So before we can look at the examples, let's some simple exercises to verify. CC infinity, please verify that it's a vector space under the usual addition and scalar multiplication. It's a vector space over R, okay? Vector space over the real line because we have taken real valued functions, okay? Now, another interesting exercise that you should check is that, and try proving this, is that I've already said 0 belongs to this. Any non-zero function of CC infinity omega is not analytic, cannot be analytic, right? You already know, right? So when you talk of infinitely differentiable function, right? There is a subclass of function here which are usually denoted as CW. Subclass here, these are analytic functions. What are analytic functions? These are the functions these are infinitely differentiable functions where its power series converges to the function, right? So it admits power series expansion, and you know that so in the real variable situation, not all infinitely differentiable functions are analytic. And what is this exercise telling you? That the compactly supported function is actually outside the class of analytic function. If it is outside in the sense that it is intersecting the analytic function only at 0. So 0 is the only common element between CW. So if this is analytic class and if this is CC infinity class, 0 is the only element sitting in the intersection. Every other element of CC infinity omega is not analytic. That's an exercise that you need to prove. And that's an important, which is why if you can actually think of an example, if you try to think of an example for this, it is not immediate. You cannot very easily obtain a example because most of the examples that you can imagine are functions which are analytic. So if you have to look for elements of this class, you have to go outside the class of analytic functions. I mean, non-trivial example. Okay? So that's what we are going to do. We seek smooth non-analytic functions in CC infinity omega. Okay. So what is that we want? If you actually imagine, even in the case of one dimension, you are looking for functions which can go up in some compact set and should fall down to 0. And it should fall down to 0 nicely, smooth, in the sense that it should not break the differentiability, because you need infinite differentiability in omega. So it should fall down to 0 in a nice way, right? In a smooth way, right? That is the kind of function that you want, that you're looking for. So do you know any function which where I can, for instance, what I'm saying here is that I can take two functions and take the zero function, right, and then just attach them at the boundary of the compact set K, let's say, right? But I have to attach it in such a way that I don't break the smoothness, right? So, in other words, looking for examples of functions is like, it's like trying to glue the zero function along the boundary of the compact set, right? In this case, I called it K, compact set with smooth function inside the compact set such that the smoothness is preserved in all of domain, right? I want to attach the zero function at the boundary of the compact set in such a way that the infinite differentiability doesn't break. And that's not a very easy thing to do, because for instance, I can take on the positive real line the y equal to x, and on the negative real line the y equal to minus x, right? And I can join them here, right? This is like gluing two functions. This is y equal to x function, y equal to minus x function. I have glued them together at the point 0, right? And what do I get? A non-differentiable map, which is mod x, right? So gluing always doesn't, it's not even gluing. Attaching in such a way that you don't break smoothness is very important, and that's again not something that you can do very easily. For instance, you can also, like, for instance, if I take two functions, let's take an interval AB, let's say, and let's say outside B the function is 1, and outside on the right side of B the function is 1, let's say the value is 1, value of the function is 1, and on the left side of A the value of function is, let's say, minus 1, right? Let's say up to A and up to B. Then I can, of course, I can put a function here such that I can extend this function inside AB, the interval AB, in the open interval AB, I can extend them such that I can make this a continuous function, right? I can just have to draw a straight line like this. So you have this, you have, let me draw it properly, too much of overwriting, right? So if I have a straight line here, okay, then I can just make this join, right? So I can do this inside this, and I've made this a continuous function, but I might have introduced non-differentiability at these points, right? All these are gluing two functions such that, but then how do we do such that at this point of gluing I don't break the smoothness? So if you know partition of unity, that is one such way of gluing smooth functions without breaking the smoothness of the function. So here let's, without going to make it quite simple, let's try to see, can you think of a function which is which behaves like this, right? It can go to 0 smoothly without creating without actually falling smoothly to 0. Then by attaching 0 at the boundary, I may not be breaking any smoothness. So you actually know one such thing, which is actually the function, which is the function e power 1 over x. If you draw the graph of this function on the entire real line, you will know that it has a kind of discontinuity at 0, because if you approach it from the right side, it blows up, it goes to infinity. It's like this. If you draw the line suppose this is the line, okay, so, and and then it has to come like this. Something like this is how the graph will look, alright, for this. So there is some problem here with this function. It has a problem at z, but everywhere else except at this point, 0 point, everywhere else the function is infinitely differentiable. And the catch is, forget about this, but the catch is at this point here. This is infinitely differentiable and it's very nicely going to fall down to 0 here. Okay. Okay, so that is the kind of one example that you are looking for, that you want a function which falls to 0 in a smooth way. Okay, and that is e power 1 over x is one such function for whenever x is negative. So we are going to tweak this function to obtain some examples of the cc infinity omega. Okay, so this is the Cauchy's exponential function. There are actually many, this is not the only thing, but this is what we will choose, but you can always take e power minus, a different situation, but here the idea is that because you want to attach at the boundary of the compact set, so here you take x for positive x. For x positive, it is on this side is exponential of minus 1 over x square, and on this side it's 0, right? So here it's 0, and this function, as we have seen in the previous example, near 0 will fall to 0 smoothly and will come and attach to 0 smoothly. This behaves like x power, so x 1 over x square is always positive, so minus of that is negative, which behaves like e power minus 1 over x. Okay, and that is infinitely differentiable, and this is not an analytic function as we have already seen. Okay, so this is one example. This is an example of a function which falls to 0 smoothly. So using this, one can create functions which can fall to 0 both sides on the boundary of, let's say, a compact set K. Right? We just have to use these functions. Okay, so in higher dimensions, what do we do? So take Rn, take a ball of radius b. So you have Rn, you take a ball, suppose this is Rn, you take a ball of radius b. Okay, then mod x less than b is inside this ball, and mod x greater than b is outside this ball, including this boundary, right? So here what you just take this function, wherever you have x, you replace that with mod x by b. Okay, and then what you get is this function. So if this function, if you actually see, this function will be a function which is supported inside this ball, and outside this ball it is 0. Okay, it's outside this ball 0, and it's going to fall at the boundary of this ball to 0. This function is going to smoothly fall to 0. Right? So this is, so if you draw the graph of this function above this ball, you actually have a bump above this ball and then falls down to 0. That's an example of a cc infinity Rn function. Okay, so using this, one can actually create a family of functions which will be very, very useful when we study density regularization and so on, which is called with sequence called modifiers. Right. So in the previous example, instead of wherever you have b, if you take the ball of radius epsilon, for each epsilon, you set an epsilon, and make the radius of the ball to be epsilon, then if you take this function, see, because it's for epsilon, I am calling this f epsilon. Okay, so f epsilon is precisely the function that I have there, and I'm just integrating that because outside the ball it's 0, so the integral is supported only in the inside of the ball, which is this function. Okay, now you do a change of variable, that is y equal to x over epsilon. If you do that, then this is the term that you get, and this measure here will give you epsilon n d. So dx will become epsilon power n dn because you are now in n dimension, right? So you will get for each phase you will get one epsilon, so you get epsilon power n. Now this is just some number. You just call this number as, say, some C inverse. Just call it as 1 over C. Okay, if you call this as 1 over C, this one, then what you get, and if you define your rho epsilon to be this term, you bring it here. So C epsilon here, and call that as rho epsilon. So what you have shown here is integral of rho epsilon is equal to 1. Okay, and rho epsilon is just scaled function of this f epsilon, and it is still in CC infinity of Rn, right? So rho epsilon is this function which is supported in the ball, which is supported in the epsilon ball, and it's a CC infinity function such that the integral of rho epsilon is 1. Okay, and this relate this to the condition 2 of what Dirac had obtained, right? So integral of the Dirac measure has to be 1 now something. So this is something more or less. So this is actually what is called a Dirac sequence. Like later you can, if you have come across the word Dirac sequence, it basically means that a sequence of functions which converges to the Dirac measure. Okay, and this is a Dirac sequence. In fact, if you have come across if you have done some C-star algebra and other things, you must have come across the notion of approximate identity. This is something like an approximate identity in some C-star algebra. Anyway, let's not worry about that. So this sequence will be very useful. These are called sequence of modifiers. The English word modify, modify means kind of to pacify, right? To make something nice, good, right? I mean, you have to pacify. Someone is in a bad mood, you try to cheer him up and bring him in a good mood, right? That kind of. So modify is in that sense. It is this will be a function sequence which will be very much used to make a badly behaving function, basically smoothen out bad functions. Okay. Now let's introduce this notion of multi-index notation, which will be useful in the course that we will do. I mean, whatever, since we are going to do partial differential equation course and Sobolev spaces and so on, we are going to deal with partial derivatives. The notation for higher order higher dimensional derivatives is very useful. So if you can recall how you write your k degree polynomial in one variable, it's written as summation AIXI, right? That's how you write. Is a polynomial in k degree, you write up to, let's say, k. Okay, this is how you write a polynomial of k degree, right? So now if you want to generalize this to higher dimension, how do you write when you take n variable, right? So here the x was one variable, now your x is n components, let's say. In this case, how do you write how do you write a k degree polynomial? So the simple way to do that, if you have not seen, is using the multi-index notation. Here it's a alpha x power alpha summation mod alpha less than or equal to k. So basically a alpha are just the coefficients, it is just indexed by alpha, but point here is alpha is an n tuple. The x power alpha is the power of, so x itself is a, as I said, is an n tuple. But alphas are tuple of integers, positive integers, right? Whereas these are tuples. So x power alpha is x1 alpha 1, x2 alpha 2 product, this product, so on up to xn alpha n. And what is this mod? Alpha is nothing but the sum of these alphas. So if you introduce this notation, this notation, and this notation, this or this describes a k degree polynomial. So this is the multi-index notation. We generalize this to differential operators, partial derivatives. Okay. So as I said here, alpha is a multi-index n tuple where alpha i's are non-negative integers, and then mod alpha is this sum, and x power alpha is this. Okay. Using this symbol, one can write down a partial differential operator. Here, of course, we are assuming that the mixed derivatives are same. So you know that for smooth functions, the mixed derivatives are same. So we are more or less working with smooth functions here. So we don't have that issue. So the alpha order derivative, partial derivative, is given as, since alpha is a tuple, alpha 1, alpha 2, alpha n, x1 power alpha. So the alpha 1, the x1 derivative, alpha 2, the x2 derivative, and so on. So this is written in this form. Okay, this is mod alpha where you have summed them. So that is a notation you use for the partial differential operator of order alpha. Okay, so once you can see that when mod alpha is 0, that means that if the sum is 0, since each of them is a non-negative integer, positive integer, if the sum has to be 0, each of them has to be 0. So the mod alpha equal to 0 corresponds to taking no derivative. So that partial derivative means no derivative. Mod alpha for k belonging to natural numbers 1 to n, you can accumulate all mod alpha equal to k. Okay, all first order. So k equal to 1 means all first order partial derivatives is called d1. All second order partial derivatives are called d2, and so on. You can accumulate them. So what is k equal to 1? K equal to 1 is the all first order partial derivatives, which is usually what you know as a gradient vector. So this d1 is nothing but the gradient vector. That collection, all first order partial derivatives. All second order partial derivatives is what is called the Hessian matrix. It's all second order partial derivatives. Okay, and so on. Okay, so now you can, once we are here, you already know that the Laplace operator is nothing but the trace of the Hessian operator. If you sum them, if you sum the diagonal element of the Hessian matrix, that's precisely the Laplace operator. In terms of the gradient operator that we introduced here, Laplace operator is nothing but gradient dot gradient. Okay. Okay. So with this lecture ends. It was a first lecture, so I don't know completely. I don't know how it went. Let's anyway, it's a motivation lecture. We have not done much here. We have just motivated you to the course, why we are doing this course, and what are the stuffs required. So let's meet in the next lecture. Probably the lectures will become much more rigorous in due course.